The Susan Mahan Niebur Early Career Award is an annual award given to an early career scientist who has made significant contributions to the science or exploration communities. Recipients of the Susan M. Niebur Early Career Award are researchers who are no more than 10 years from receiving their PhD, who have shown excellence in their field and demonstrated meaningful contributions to the science or exploration communities. Susan Mahan Niebur was a former Discovery Program scientist at NASA who initiated the first ever Early Career Fellowship and the annual Early Career Workshop to help new planetary scientists break into the field. This year, the prize is jointly presented to Dr. Shuai Li and Dr. Parvati Prem. Dr. Shuai Li is an early career scientist who has already made significant, high-profile contributions to the science and exploration communities. Just a few examples include helping to reveal water content in lunar pyroclastic deposits, providing key insights into the formation of water on the moon's surface by studying abundances in magnetic anomalies, finding the first direct evidence of surface exposed water ice in permanently shaded regions on the moon, and finding widespread hematite at high latitudes on the moon, identifying an apparently novel and very exciting formation process. His research not only appears frequently in prestigious peer-reviewed scientific journals, but has also captured the interest of the general public and has been picked from the journals for coverage by general media outlets, including ABC, BBC, CNN, the New York Times, and many more. As an assistant researcher at the Hawaii Institute of Geophysics and Planetology at the University of Hawaii at Manoa, and a member of SSERVI's ICE-50 team, his research focuses primarily on two different areas: studying water and its associated processes on airless, rocky bodies, and studying the non-icy components on icy bodies in the outer solar system. His research is helping to constrain and quantify lunar surface properties like the composition, retention, and distribution of water ice at spatial scales ranging from micrometers to kilometers, revealing surface processes possibly associated with solar wind implantation, impacting of meteorites, comets, and interplanetary dust, as well as interior degassing. His research on the distribution, variation, and origin of volatiles on the moon and asteroids is improving our understanding about solar wind, volatile delivering impacts, and magmatic and space weathering processes. As an early career scientist who is changing our views of the moon and the formation of the solar system, and changing those views from the perspectives of the planetary science community, the exploration community, and the general public, Dr. Shuai Li is certainly a very worthy and deserving recipient of this year's Susan M. Niebur Award. Congratulations, Dr. Li.
Thank you, Brian. Thank you for the so fruitful introduction. I was totally shocked, surprised, stunned as same as previous several awardees. It was like a few weeks ago. I was with my 4-year kid in lab, and suddenly Greg called me. I cannot believe it. Suddenly I feel like I was not forgotten by our community. Because we know, like scientists, we always do science like silently, quietly all the time, right? So suddenly you can feel the warmness from the community, give you even stronger encouragement and power to work to continue. So yeah, first I want to thank my nominators, even though I don't know who you are, and also I want to thank the committee of this award for awarding me, and also I want to thank the community, recognizing my work. Without the pause from all of you, I kind of make this achievement, particularly my graduate school training at Brown University, and also the postdoc opportunity at Hawaii. So I really want to thank everyone for all these kind of supports. One mankind cannot achieve such achievement without support from people surrounding you. So as Brian just introduced Dr. Susan Niebur, what she has done to the community, I was amazed, and I hope to contribute more about her what she has done to the community, to encourage people, to help people, to inspire people to continue their exploration in planetary science. So I want to share some of my very limited science experience for our young fellows, particularly the senior graduate student and early postdocs. Hopefully you can get something from my experience, and hopefully you can get more products and more fruits from what you are doing or what you want to do. Like I said, I want to introduce some of my very limited experience with our senior graduate students of early postdocs. So based on my experience from graduate school to now, like 5 years after a PhD, I feel time in the last like 2 or 3 years of 1 year graduate school and a first 1 year or 2 year postdoc time, the time is relatively sufficient in comparison to as you become senior and senior in a career, because you're going to make more commitment to like a service, not only research. So I would say if you can try to pick 1 or 2 like projects, like high risk and a high return project to do. At this point, I want to say, like as Paul and Tim and Darlene mentioned, encouragement at this time is particularly important, because as a early career or like a senior graduate student, you do not have much experience in research. So it's like you definitely need encouragement from people from you. But at the meantime, I also encourage you to trust your own scientific intuition and also your own innovation, because sometimes like you are the experts in your field, and sometimes people around you cannot understand what you really want to do. So you have to trust yourself. Trust yourself. Sometimes you don't have enough support, but you have to trust your scientific intuition, so you can gather more and more evidence for what you want to do, and also trust your own innovation. And you may want to take the risk to try, because as I said, this time could be the most sufficient period. Time is relatively sufficient at this period. Otherwise, when you pass this period, you may not have enough time to do what you want to do. But even though you have a high risk to fail, you will gain more or less. So trust me. So yeah, so take the risk to try, trust yourself, and eventually you will gain more or less. So I have 2 examples about my research to share. The first one is about the discovery of surface exposed ice on the moon. So first, after my thesis preparation, I have some free time to do research myself. And at that time, I feel like I don't want to waste the time, so I just pick up a topic that interests me. Well, this is inspired related to my PhD thesis. I want to know whether there is ice on the moon, and then they pick up a topic, and then you can review literatures. So this is like reviewing those literatures will give you confidence to what you want to do. So like then I also help you to assess like major unsolved problems. So for example, for my case, like I just read roughly like 400 papers, and finally I did a summary of the table. You don't have to go through it in detail, but the short sentence is like, any surface exposed water ice in lunar PSRs where the temperature is cold enough. So from all the paper I've read, it tells me yes, probably, or sometimes even no. So like it's not a confirmative answer. You cannot get it from it. So that's the problem. That's the question you want to address. that I want to address at that time, and then I choose, or you want to choose approach or data sets or experiments to solve your problem. So for me, I choose, at that time, I have the data set in my hand, like the moon mineralogy mapper data, because it measures reflectance and also scatter light from PSRs in the spectral range from 0.4 to 3 micron region. And as we all know, water ice showing very diagnostic absorption features at the visible to near region, as I showed in the left plot. The black curve, this is the global average M-cube spectrum. You can see it's redden. It's relatively featureless, maybe very weak 1 or 2 micron absorption feature. And a 3 micron feature is due to hydroxyl. And the blue curve is the pure water ice. You can see these features. It's very unique diagnostic compared with the typical background. So then I decided to use this tool to search for ice on the moon. And it turns out the spectra in PSRs are totally different. You can see from this movie, I collect some data. You can see it's quite a very noisy actually. It's almost like a random noise. But I didn't quit. As I said, at that time I have some time and I want to do something. And also, I really want to know the data set, how the instrument performs in the PSR, like very dark regions. And I checked this kind of data for 4 months. I'm not sure you can believe it or not. I'm not sure Carly still remember. It's a great fortune to work with the PI of the instrument in the same institute. So at that time, I sent tons of emails to Carly to ask her, like, what do you think of this spectrum? All weird spectra to her. And I almost got the same answer, artifact. So like she sent me back tons of emails saying artifact, but I didn't forget. I didn't quit, and until I found something I showing on the red figure. It's like, even though it's noisy, but you can see the trend, and in comparison to the pure ice. So the dashed line is kind of smooth or average. You can see like the trend follows this well. And when I sent this figure to my postdoc advisor, Paul Lucy, I think he was shocked too. I still remember the email he sent back. So, but this is not enough to convince, still not enough to convince a lot of people. Like, even though I saw this kind of patterns tons of times, but a lot of people still were not convinced until I got this figure. This is like all pixels put together. So like raw data without any processing. And then in comparison to pure water ice, this looks like, almost identical. And suddenly like all my co-authors and people around me, they were convinced, and then came out of this work. Yeah, so I agree with what Paul Lucy said. You want to insist what do you want to do, and you should trust yourself. And even though you cannot find anything, I have a friend, he told me, hey, examine white noise for like a few years, but at least you know the data after your work. You know the data. You know how to identify white noise, at least after you spend much time. So you will gain more or less, even though it's high risk. Another example is I want to advise our young fellows, like you want to be sensitive to your data and or your approach or experiments. So for my case, it's like my data. You wanted to record or frequently revisit the anomalies. So I mean, the anomalies is something that doesn't make sense to you. So you don't have to know the answer at the beginning, but you wanted to record and frequently revisit those anomalies, because as we know, new discoveries are commonly associated with anomalies. And this is one example. So this is the M-cube spectrum. This is one spectrum raw data from the polar region. When I saw this spectrum, I feel it doesn't make sense to me. I'm not sure any like a lunar spectroscopy can tell why this doesn't make sense. I want to point you to these two bands, like two features, because normally we don't see this feature. And for this feature is normally near 1 micron, but this is too short. And also you can see the strong suppression in the visible part. So as a spectroscopist, you can tell immediately there could be like indicating like a strong charge transfer. So at that time I don't know what's going on. But I often revisit what this data and I compare it with like a global average. It doesn't match for sure, right? Because as I said, it's anomalous to me. It doesn't make sense. And then I compare it with for sure it's not mineral. We know it's not like a typical pyroxene, olivine, or plagioclase. And then I compare with the glassy components. So you can see it doesn't match either. I feel okay, there must be something new because it doesn't match with other, the animals we know on the lunar surface until I compare with the pure hematite spectra in the database, as the blue curve shows. And after continuum removal, you can see the feature that almost identical, match very well. So it's indicated the presence of hematite. And then we came out of this hypothesis about the hematite formation. So when the moon was in the Earth magnitude, the magnitude helped the moon shield tons of over 99% of the hydrogen. But at meantime, the solar wind can blow oxygen from the Earth's atmosphere onto the lunar surface. So it's provide a relatively oxidizing environment to oxidize iron on the lunar surface. It's still a hypothesis. I will need more work to demonstrate. Yeah, so that's my two experience. So hopefully you can get some inspiration from it. Well, very limited. So I have to share more. But if you have any questions, please contact me. And I wish you best luck to your adventures in science exploration. That's it. Thank you.
Thank you so much, Shuai. And wow, you have an amazing career ahead of you. It's it's just such a privilege getting to work with you through SSERVI. So thank you so much, and congratulations.